is agile. We're planning things as we go. So, already got lots of feedback on the book on our website. Brilliant. Thank you very much for that. And we've learned a lot in 5 minutes, which is cool. Thank you for being guinea pigs. So, yeah, overview of the level 3 standard. In fact, just a very quick overview of everything. If you go to Wikipedia and say what is computer science, then it gives you this list of computer science. And there are a number of lists of what topics computer science covers, but the whole point of computer science is to enable us to do really complicated things with computer programs that you couldn't do without having structures like the finite state automaton that we had before. So those finite state automaton do amazingly complicated things, just using a few, well, they're not actually arrows and circles on a computer, it's actually arrays with this thing saying where to go next, but it's a very simple structure that can do very powerful things. And all of these, the whole idea of them is that they will enable us to make computers run faster, because speed is really important. Those who've done HCI will know that 0.1 of a second is too long, well, almost too long in an interface. They enable us to do things that are intelligent or have good interfaces, things like that. And otherwise, if you get programs that are just written without this knowledge, then they tend to be slow, they tend to be painful to use, or by good luck, they might be fast. And the other thing is they have to be scalable. You might have 1,000 customers today, but you might literally have 1 million customers tomorrow. Your product or your site or something might go viral overnight. And if you're using algorithms and systems and networks and things that can cope beautifully with 1,000, but not with 1 million, then you'll have exactly what happened to that regex thing that we had, which is that people go, oh, it doesn't work, I'll never use it again. And even though it's a brilliant thing, right? So it's really important to have, that's where these things come from. So here's one list that a crowd has put together. Information encoding theory is in the level 2.44 standard. Okay, it's compression and encryption and error correction. Algorithms is in the level 1 standard, 1.44. Programming languages in the level 1 standard. Artificial intelligence is in level 3. Computer graphics is there. Computer security, it's a mixture of level 2, but also the level 3 network stuff. Security is a part of networks as well. Because networks are about, well, I'll talk more about it later, but it's about not just getting the thing through, but getting it through in one piece. And making sure you know that it came from the right place. And software engineering. And there are a few things here that aren't quite covered. Computational science, for example, or health informatics. Perfectly valid to cover, but there's a limit to what you can do. Now, the way the standard works, and there was a copy in the pack that you got, is that there are 6 topics, and these are basically the main 6 that your students are likely to be able to get their heads around that haven't been covered at level 1 and 2. And the one that you probably just about got up to merit level in just then was formal languages. So you've got to write a report. And so hopefully now you've got a rough idea what formal languages might be, and I've mentioned what the other 5 are. But when you look at the standard, the bullet points, extracting the keywords, the student has to write a report, maximum 14 pages. From the research we've done, about 10 is plenty. And one person got excellence, I think with 6.5 pages or something like that. It's not length that counts, it's does the student understand that concept. If you put up a finite state automaton and explain beautifully exactly what each link is in a paragraph, that's it in 1 page. You know. So for the standard, they have to have key problems, and by the way, the use of plurals in the standard needs decoding. So it says they will explore areas from computer science. There are 6 possible areas, but for it to be plural, they have to do 2. Okay? So effectively, pick 2 of those 6. Now, who picks the 2 is a big question. In the end, the examiners, or markers, whatever they're called, they are looking for a report that touches on 2 of those 6 areas, and they won't know who chose them. So especially when things are starting off, it may be that you will limit it to a particular 2 or maybe 3 for them to choose from that you're comfortable with. And we were just talking, I was talking with a couple of people before, I think it will vary enormously between classes. you had a little look at the computer graphics thing before, for example. If you've got a couple of students in your class who are really into maths and they could learn matrix algebra, in a minute and things like that, then you might say, look, you can do that one as your thing, I'll guide you through it, but I'm not teaching it to the whole class. And maybe even you could work with the maths teacher on it if you've got a friendly maths teacher who's interested in that sort of thing. The ideal, I think, would be at least to expose the students to all 6 of them, because of course you don't want to teach exactly to the standard. Like, I'm going to tell you the absolute minimum you need to get through the standard. And what would be kind of okay, I think, would be that video that we did about AI. We'll have 6 of those, and if you were to either play those 6 or give your version of them or have discussions about them, say in one period, then that's exposing your students to the range of things that computer scientists are interested, and hopefully, even after seeing that video, you sort of know some of the issues that people think about with AI and why it's used and so on. It's probably a wee bit confusing having silly robots jumping around and that, but remember the whole goal is for them to know the breadth of the topics anyway. But then you might say, these are the 2 that I've chosen that we're going to work on this year. What would be a little better but harder, depending on your background or how many years you've been doing the standard, which obviously will be 0 at the moment, is you might say, well, there are 3 or 4 that I'm comfortable with. If you pick one of those, you'll get more help. And long term, it may be that all 6 of them you can support students doing. There might be 1 or 2 that really you're not that strong on, but if you've got a student who can do it on their own, then that's fine. So, and then the key problems, the plural there, is that there must be a key problem. There must be at least 2 key problems, and because there are 2 topics, that means 1 key problem from each topic. So the absolute minimum they could do is find 1 key problem in formal languages and say 1 key problem in AI. Okay, so let's pretend that you've chosen formal languages and AI as the 2 topics you're prepared to support. So so what's a key problem in formal languages? Well, one of the key problems is reading input and saying if it's correct. Okay, and so they could do an example on that. This is absolute minimum. It would be nice if they did a little more, but in the end, to achieve the standard, the marker will be saying, have they done a key problem, and have they shown understanding of it? And showing understanding doesn't mean copying the Wikipedia or paraphrasing Wikipedia. It means showing a personal experience. So one of the things that has come through from the projects is student voice. Heard that over and over. The markers want to see the student voice. They want to hear that the student has done it. This is my finite state machine that I put together using the software from this site, and this is how it works. And you can see even with the A's and B's, there's an infinite number of possible finite state machines, so there's no reason that any 2 students will use the same one. They shouldn't just pick the first one in the book, put it in and try and explain it. They should make up their own, explain what their one does, how you get to their own. It might be a map of their city. For those who went on the earthquake tour yesterday, there's a finite state machine around the eastern suburbs because there's only certain places you can get to and from, and you can't always go back to the same place and things like that. You can do a finite state machine of your area of town or something like that. And there's lots of ideas in the text on how to do that. But something personal, here's my house and here's all the places I can go, or here's my bank account number, and which has to have 4 digits, a dash, 2 digits, a dash, and so on. And here's a finite state machine that says a digit, a digit, a digit, a dash, and so on as the transitions in the finite state machine. This one will check bank account numbers for my bank, and that's probably a bit less personalised because there's not that many banks. But there's so many examples, and there's lists of them in the textbook that they could use. And then, so the next thing that's in the criteria is that there need to be examples of practical applications, and that's exactly, well, that was a practical application. Someone's typed a date into a website. How can you check that it's a valid date? Maybe it has to be dd/mm/yy, so is it digit, digit, slash digit, and so on, and are there restrictions on which digits can appear where? And here's the finite state machine that I put together that does it. The key algorithms or techniques, finite state automata, are a key algorithm or technique in formal languages. Okay, they're a fundamental thing that just comes all over the place with anything that's processing input and deciding if it's valid, okay, or deciding what it is. So when you type a computer program, that will be fed through a finite state automaton, and that machine will say, oh, they've just done an identifier, they've just done an if statement, oh, there's an equals here. And then the compiler makes sense of that. That's a slightly more technical application of finite state automaton. Some of your students might be interested in that. You could write one that can detect if you've got an identifier in your particular programming language. So the way that would work would be, we start here, we haven't seen anything. What's the rule about identifiers in programming?
Start with letter.
It has to start with a letter, okay? So if I get a letter, is that a valid identifier, like just X? Okay, and the double circle, we didn't quite get up to this, but a double circle, that's suburbopolis, that's the goal, that's what you're trying to get, okay? So, if I start here and you tell me I've seen a letter, that's okay. What if I get another letter? Is that okay? Mm-hmm. Right, so in fact that train just goes from the goal place back again. And so, and what if I get, say, a digit here? No, okay. So a digit goes off into Netherland, and no matter what comes next, we stay there. And so now, I'll give you a sequence. A, B, C. A, B, C. Yes, it's on a double circle. Okay. 1A. 1A. No, it's not on a double circle. It's not an identifier in the program. What about A1? Whoops, I haven't finished my finite state. So what do I need here? Where's it going?
Towards
Yeah. So that's almost the finite state machine that is reading your programs in and checking that your identifiers are valid. Okay? Someone had to design one. No, it's not quite, because you know that there's other things you're allowed.
Would it need a space before you got to the double circle? Would it come off the double circle with the space to the end? Because you have to have a space afterwards.
There must be a space to know that, well, or an equal sign, or a, you know, so it starts getting complicated. Yeah. So, and again, things are a little simplified here, but that at a student's level is enough to say, this will tell me whether or not I've got a valid identifier for my program. Yeah. And you're right, it's like, when you get to the advanced level, you have to think about how to tell about the context and what's coming after it and that sort of stuff. And that really exemplifies what we're doing. Hopefully that's enough for you to see that they're useful. If that's interesting, go off and do computer science and find out how to really get it right. Yeah.
That's going to be a standard answer. I have a button on the desk for that. If you find that interesting, go do computer science and get a real answer.
Yeah, so someone pointed out that nearly everything we teach in schools or even at university, well, it's not quite fair to say, is wrong. It's not quite right. It's not the whole story. And we find this in our first year courses. How much do you actually hide from the students? But the cool students, of course, ask you those questions, and then you go, that's a cool question, here's the answer, or you go figure it out. Or whatever. Yeah. You can do the same thing with, is it a valid number? Okay, so we'll just very quickly do this. Okay, so I'm starting here. What, if I get a letter A, is that a valid number? No. Okay, so letter A this time goes off to Netherland. We will never come back. What if I get a digit?
Yeah.
Okay, so a digit, in fact this is all letters go there, and that's a double circle, because just one digit on its own is a valid number. Okay. What if I get another digit?
Yeah.
Okay. So now your student could draw something like that and say, 1, 2, 3 in a row would be 1, 2, 3, and just explain which steps it's going through. It ends up as a double circle, so my system says that the digits 1, 2, 3 in a row counts as a number.
A decimal point?
A decimal point, where does that take you? Can I just go like that? No, because that would allow 1.2.3.4 or something, or 1.3. So now we go off to another state. Is 3 dot valid? Can I make that a double circle?
Yes.
3 dot. Dot to digit.
Yeah, it might depend on your language, but a lot of language 3 dot is okay as a number, and others it's not. So now this is where it's personalised. I'm learning this language. I type this number into my language, and it comes up as a syntax error, or I type it into this language and it accepts it. Okay. And now they've really been and this is why it's called formal languages. So these are all languages. These are sequences of things that are allowed in your language. But it's formal because it says, I am going to give you a bad day if you have 1 dot in the wrong place. Okay? That's what formal language is about. And anyone who's written programs know that They are very formal. It'll either be in or out. So a dot takes you to a different place that may or may not be okay, and another digit is okay in that place. And by the way, we haven't done positives and negatives because the first character could have been a positive or a negative. But you can't have lots of them, right? And again, this is a very simple one for unsigned numbers we've just put together. Signed ones, with plus and minuses, a little bit more complicated, a bit more explanation, and more opportunity to talk about key techniques, and especially evaluating the effectiveness. This is the last thing they have to do with whatever they've picked out of these standards. So how effective is this? Well, it doesn't do positives and negatives. On the other hand, it's very fast, very simple. There's different things, and so again, sometimes the effectiveness of a concept or a technique will be how fast it is. One will be how many states you need. Okay, you imagine writing a program without using this concept that could read in any input and tell you if it was a number. It would have all if statements and stuff flying all over the place. It would get really complicated. But if you can do it as a finite state automaton, and then you can throw that at a program and it'll just turn that into a program for you, you're really confident it will work because you've got a simple model of how it works. Very technical. This is the stuff that compilers are made of, but it's also what happens when you type a credit card number into a website or a date into a website. It'll be fed through one of these, and usually within the browser. It's not called that, it's actually called a regular expression. Okay? And we touched on regular expressions on that website that didn't want half you to use it. A regular expression is another completely equivalent way of doing that, but what happens is you put in the regular expression, it gets converted to one of these, and it will check it. And further down in the book, there's actually some software that you can type regular expressions into that will get converted to these. And then your students are really dealing with multiple things here. They're saying, okay, I said it has to be a letter followed by any number of letters and digits. That's what a regular expression can say. And sorry about the jargon, we haven't really done this in great detail. And that produced this finite state automaton for me. And I can see this loop here is the bit that deals with digits that come after decimal points. Okay. That would be excellence. Okay? Right. So for any particular thing, really it's just one key problem, examples and so on. So, now let's just quickly go through the 6 topics. Formal languages, so you've had a taste of it. Key applications are for programming, for markup, anything that's parsing input, checking syntax, regular expressions. Way beyond what I'd expect, but some of your students might be interested, grammars, which are like very powerful ways of describing not just how an identifier is, but how a whole Python program or a whole Java program, the rules for the entire program. Okay. And there's the finite state automaton. One of those would be a key concept that they could talk about. This is the guide, and I've actually given it to you in the handout, so if you look up formal languages, I think they're in alphabetical order, then again, this is the guide that should come out tomorrow. Which talks about, so here we go, regular expressions are one of the concepts in finite state machines. Another word for finite state automatons of machine. So as soon as you spot that keyword, as soon as your student has done that, about that keyword, they're pretty much there. But you'd want to give them the big picture. And so, again, there's a video at the start, there's an introductory thing, there's this thing at the end that it says, hey, here's what really goes on, this is what we didn't tell you, and so on. So, for example, parse trees, just to, okay, now I'm going to throw lots of jargon in a short time, okay? If this is really getting too much, it's all in the book, and remember, you only need 1 or 2 of these concepts for your students.
As long as you're under 10 times lost, you're all right.
Yeah. So a parse tree is a way of, so this is HTML, and all it's saying is that an HTML document has 2 parts, a head and a body. And this is a particular, it's this HTML document, okay, which is actually, I grabbed off one of our home pages. And then cut out lots of stuff. Actually, sorry, yeah. It's basically, the body can have multiple divisions. This particular one has got an H1 and H3 in these divisions. If you have an unordered list, it consists of 3 list items. Okay? So it's actually just a breakdown at each layer. And that is a really valuable technique for dealing with complexity in a formal language, whether it's a programming language or HTML or XML or anything. So anyone who writes programs that reads in XML, like if you write in a web browser or lots of systems use that, they'll probably have a parse tree in there somewhere that's trying to make sense of the particular HTML and stuff.
Please note that if you're also teaching one of the digital information or digital media standards, where you're talking about HTML, maybe you've done that first, they've done all this, they've written some code and say, now let's go and look at what you wrote. They might be able, for example, to take one page that they wrote. If they wrote a little page with some HTML, say, we could describe the parse tree of that page. And here you've got that personalization. It's my page. Here's the parse tree showing how it broke down. And you've then got that same thing you've talked about over there, reusing it and extending it a little bit to give you this.
That's a very good point. And so take, for example, computer graphics, where we're talking about how things are rotated in an image. You might be doing a media thing where they're using Illustrator or Photoshop or something like that to move things around. And rotating is something that you do in PowerPoint, for example. And then you can go across there and say, oh, here's the mathematics that PowerPoint is doing when I grabbed that thing and made it rotate. And now you've done 2 standards. But yeah, the background, the understanding, the applications, because remember one of the things was examples of practical applications. Well, rotating things, they've probably done it. Who's got a student who's never rotated an object on the screen? So yeah, making those connections helps. And this applies to all the standards. They're isolated just purely for practical reasons. None of these happen in isolation. AI uses formal languages. AI will touch on complexity and so on. They will.
With the HTML one, my students often forget to close the tags, so that would be a good way to help to remind them to close the tags, because the closing tag, you go back up the tree again.
Yeah.
So if you haven't closed the tag, then you're down in there and it will look funny.
One of the fun ones that we use is here's another finite state machine and how it might relate to making sense of input and language. And I haven't met a class yet who instantly are putting together sentences and things. And the only goal is that you have to get to the double circle. So one of the questions is, are we allowed to say the friendly monster? No, because that friendly monster doesn't get to a double circle. So that's not valid in this language. It has to be the friendly monster sang or danced or something. Except that's what's happening in formal languages with computer programs. It's saying, hey, you've left something off, you've forgotten to close the tag, or something like that. Not necessarily using finite state automaton, but hopefully that can help with the connection. Okay, I'll spend a bit less time on some of the others. Network communication protocols are about reliable communication. Threats and failures, they are keywords that you'll find in the description. So how is it that when you, say, do a request to google.com and it hops through all of these points, that you always get something back, because it might actually get lost in the process. And so your request, when you type Google into your web browser and it goes out, if something fails along the way, it's still going to come back. So how did that happen? What was going on under the surface to make sure that things that are lost go to that it goes to the right place, to actually find google.com, and that it actually comes back, and if something goes wrong, pretty obvious that it asks again if it doesn't come back and things like that, but there's a lot of tricks in there to make sure that that's going to be reliable and also secure. So it's threats and failures. What if someone else masquerades as google.com? As it's hopping around, how do you know for sure that it's actually Google that's answering you, or more to the point, checkmycreditcard.com that's actually doing it. So that's the overall of the networking, the overview of the networking thing. And we'll do an activity, I think later, we'll probably get to do it, but we'll talk about an activity later today where students can engage with that. But it's a little bit, and again, the infrastructure stuff, plug together a network, get it configured, that's very much about using existing ideas, this is really, again, let's just, when you plugged it in, what was actually going on underneath? And there'll be a lot of overlap and a lot in common. So if you're doing infrastructure, you might find this an easy one to add on to it. Complexity and tractability. This is basically about some problems take an enormous amount of time to solve. And I think for this I will just refer to the textbook because, oh, but it gives the feedback already. That's cool. Let's see.
Number 11.
Thank you. So the way that we've introduced this and
Zoom out page 2.
yeah, there we go. Thank you. This is the travelling salesman problem, which is a classic complex problem. So all it is you've got a courier van, it has to drop 5 things off. What's the shortest route around Christchurch to drop it off, or whatever. And so it turns out that this is a big question in computer science, even after about 30 or 40 years of people trying to come up with good algorithms. And the best algorithms we have, they are quite fast, but they amount to pretty much getting the computer to try out every route. Now this program does try out every possible route, which is a little bit dumb, but it will give you the right answer. So there are 5 cities, and if I press the map, and we start it, okay, it did it fine. If we give it 8 cities, it's going to take 12 seconds. Now,
4 minutes and 12 seconds.
Oh, 4 minutes and 12, thank you. Okay. This is going flat out in JavaScript on my web browser, so it could actually, we could probably get it 1,000 times faster by putting it on a decent machine, but nevertheless, that's a long time. And if we go up to 15 cities, 138 years to try out every possible route. And if we go up to 27 cities,
time for that coffee.
yeah, 600,000 million years, okay, to try out every possible route. Computers are fast, but you cannot get them to try out every possible solution and work out which one is the best, okay?
And that's only 27 cities?
That's 27 cities, yeah.
The maths on that.
The maths on that, yeah.
It shouldn't seem that long.
And that's the entire message. It doesn't seem that hard, and yet, and by the way, if we gave it a computer that was 1,000,000 times faster, would that help?
No.
1 billion times faster, like 1,000,000 times faster, how long would that take? So we get rid of those and those. It would only take 600,000 years on a, and what if I get, 1,000 computers that are 1,000,000 times faster?
So it's a premise of cryptographic keys too, isn't it?
Yeah, so cryptography totally relies on this. A cryptographic key can be cracked, but it will take that long. And none of us are worried if someone gets our credit card in 6 billion years, right? Well, the really paranoid people might do that.
But it's a whole sushi problem too.
Yeah. The maths on it, actually, it's in the book. It's probably a bit easier. And these are questions to ask your students. So if there are only 3 cities, then you could only go 1, 2, 3, 1 or 1, 3, 2, 1. That's the only order that you can visit 3 things, or 3 drop-offs for the courier thing. So there's only 2 to choose from. But as soon as you add a 4th city, if you write down all the possible orders that you could go around, it's actually multiplied by 3. Okay? 3 times as many. Because basically the 4th city gives you 3 more choices for everything that you do. And another city will give you 4 times as many choices for everything you do. And another city gives you 5 times as many. And so the maths on it basically is you've got 10 cities, it's 1 times 2 times 3 times 4 times 5 times 9 possible ways of doing it. And that is the big number that we're seeing there. Okay? It's n minus 1 factorial, if the mathematicians here. But rather than talking about factorials, we've just created this and said, kid, wait for it to finish, or else agree with us that this is a big problem. Right. So that's a key problem in tractability, the travelling salesman problem. Sometimes called the travelling salesperson problem. And again, lots of calculations they can do on this, you know, if the computer was 1,000 times longer and all sorts of stuff like that. And there's lots of games and there's iPhone apps and all sorts of things that they can play with to try this out. The bottom line is people do not use optimal rules for this, with drop-off period events. They have to make do with something that is going to be close to the best possible way because they can't afford. And you know, it's gradually improving. We're down to 3,000 kilometres for this particular thing. And by the way, there's quite a few shortcuts you can do. Like, it's not worth doing the same one backwards. You know, it's not going to be better. And there's another shortcut that if any of the lines cross, you know that there can't possibly be an optimal route. But then how do you work out that the lines cross in a computer program? So, yeah. I'll just stop that because that's actually...
So it's only 300.
Sorry, yeah.
You apply shortcuts.
With shortcuts, yeah. And it talks about it in one of the texts. Now, people have actually solved it for very large problems, but there's some tricks, and the definition of solved is a little soft. This is part of a whole lot of, basically what we call non-deterministic polynomial problems, which your students, and you don't really need to worry too much about, but you'll come across that too, maybe. Problems that are really, really hard to solve, and there are lots of them. Timetabling is one of them, by the way. Okay. There is no program that can find an optimal timetable in a reasonable amount of time. If you've got 1 billion years, that's fine. But what people tend to do is they say, I'll let it run for half a day, and we'll just have to go with that. We might have 1 more classroom than we need. There might be 2 more free periods than I'd really like to have, but we need to have the timetable ready by January, not sometime in the future. So these are all practical applications that the students can explore. They can estimate times if you try out every possible combination. And our interactives, they don't need to do the maths, they can just run it on that and measure, you know, see how. And that time is on my computer, so again, that'll be different for every student. Well, different for every computer.
Well, timetabling may be a very important application area for some of the students who weren't able to do the course they wanted. There's a place where you say, why wasn't it right? Why couldn't they do it? No, it wasn't actually the timetable teacher's fault. This problem really is hard. And they make it more understanding, motivated by that real example.
And then the idea is that instead we use what's called heuristic solutions, things that are probably roughly right, or things that are guaranteed to be within 5% of the best answer, that sort of stuff, that can finish in a second. One of the guys talking this afternoon is from Telligis. They do courier drop-off planning. They solve exactly this problem for people, and you can ask him about what heuristics or how do you deal with the exponential time problem? Be a good question for you to ask him. The answer will be simple, it will be heuristics. but then their job is to come up with good rules of thumb. So for example, you might think, oh, when you're dropping stuff off, always go to the nearest one next. Okay, that's one heuristic. It's quite good, but it's far from optimal, and you can come up with situations where it's really bad. And again, interesting exercise for your students to think about. Okay, intelligent systems, the robots and our TV presenter have already introduced those, I guess. So the name in the curriculum is intelligent systems. It's really just artificial intelligence. It's just both names are used. AI is actually more common, but intelligent systems is what was used in the ACM curriculum. It's matched up with that, and people might argue there's some differences between the two names. And actually, Pondy and Anthony are both experts on this, and Heidi, and so I won't say much, and they will be talking a lot about this afternoon. But it's about things that make attempt to do intelligent decisions. So spam detection is one that you've probably used. Is it spam or not? Humans can do that. You know, you can glance at it and, oh, that's spam. But your mail system probably is also doing that for you as an intelligent system. How is it making those decisions? What kind of structures do computer scientists use so that they can train it into, because a lot of these systems get trained, right? We say, look, that was spam, and I don't want anything that looks like that in the future. And it's not just saying anything that matches exactly that, it's anything that has some properties similar to that. And so AI is about what do we mean by properties that are similar to those. And there's all sorts of interesting questions that come up, like how can you tell if something's intelligent and so on. And there's some systems online that students can interact with, and they can argue about whether or not they're intelligent just by interacting with things and things like that. So, yeah. And then we have software engineering, which is a really interesting one because computer scientists like me say that software engineering is a part of computer science, and my software engineering colleagues tell me that computer science is a small part of software engineering. And we're both right, really. I mean, software engineering is a whole subject on its own. And essentially it's characterised by huge projects, large teams, and different methodologies for actually making those work together, and you need rules and guidelines and teamwork and how can you make this work. Now, a lot of this stuff, getting students to do it isn't necessarily the best way for them to understand it. If you say, okay, students, form a team of 10 people and build a huge piece of software to do this, then probably all they'll learn by doing that is that large teams are really hard to coordinate, which is true. That's the whole problem of software engineering. You might say, here's a methodology I want you to use, but I suspect for 17-year-olds following methodologies, I mean, we do this here, and it is really, really hard work to keep them on task, because you want them to learn about it and produce a product. In actual fact, one of our first courses effectively sets them up to fail. So the first lesson in software engineering is, here's a methodology that seems reasonable, do it. No one produces a product out of it. Okay? And now you understand why NovoPay doesn't work. And we've got lots of examples of, and it's, I mean, INSYS was another famous New Zealand one, right, the police system. Millions of dollars spent, and something that, in fact, that was thrown away in the end. Just, they never got it out. And so there's a whole lot of things in there about how do you deal with your customers, how do you deal with your team, and so on. Now, this actually sounds a lot like just a generic project, right? But I think there's a whole, rather than, so if your students have got the maturity and you've got a lot of input and a lot of time to take them through it, they could probably do a project and write up about the experience. So it's not just the project course that will get them the achievement standard. They need to talk about the key problems in the area of software engineering, the techniques that they used, and evaluate them. How effective was it? So that's not the product, it's the process. But it's very much in this context here, and probably an easier, safer way of doing it is case studies. For example, if you do know someone who is a software engineer, or you can got contacts with local companies, interview a software engineer. They might want their names changed and their projects changed. What methodologies do you use? What problems do you have? What projects have you got that ran over time? What projects ran under time and were delivered on time and on budget, and what do you think made that successful? So they're talking to one or two real people who are actually using these things and can find out firsthand how that works. Again, all of the standard stuff, these standards are kind of new. We're still figuring out the best way to teach them. We're putting forward all the best ideas that we can find, and we'll throw them in that book. But some of you may have experiences that will help, that are worth sharing. Condi.
So are we talking further about this particular topic later?
Yes, we are. Yeah. And we'll be doing an activity later on with this too, which won't involve software.
This connects to some of the generic standards, and certainly generic technology often presents a very standard, planned way of doing projects. You design and you fix your design and you build your prototypes. And it turns out, by the way, that approach is awful for software. And one of the things that comes up here is that even though this looks like generic technology, it turns out software engineering doesn't work the way other big projects do. And it's interesting hard problems there.
If we were going to complain about things in London, that would have been one of the topics that we might have talked about, actually. They try and fit around these clear holes with the generic technology.
Yes,
Yeah.
but here, this is in the skills and knowledge area, and be aware that this is not talking about standard generic project management. This is talking about the issues that come up in software engineering in particular. I love Tim's ideas of getting somebody from a software company to come in and talk and get your kids to interview them.
Yeah.
That's what our graduate students in this area do. They go and talk to companies that find out what they're doing. This is computer science.
Actually, Yanina, who did most of the material for the software engineering chapter, so the process, the generic one, is very close to what in software engineering is called the waterfall process. And you probably can't read it, which is good, you can go read it later, but she did a bunch of cartoons, and this one really illustrates what's wrong with it. But the funny thing with the waterfall process is that a lot of textbooks start with it. It was actually, someone wrote about it a couple of decades ago and said, here's a way you could do software engineering. It's really bad for these reasons. And a lot of people, including textbook authors, read the first part of it, put it in their textbook, and then the next textbook author said, oh, everyone starts with waterfall method, so I better talk about that. And so there's every chance if you get out a standard textbook about software engineering, it'll say, oh, here's the waterfall method. And it has serious issues. It has some uses, but not very many. But it's a great example of how not to do things, and if your students can articulate why it wouldn't work and what the issues are. So this is a very soft one. This would be great for a student who can interview, talk, reason about things, and write a clear article. Not a, there's needn't be any maths involved. There are mathematical approaches to this too. Software metrics, how complex a program is that you can measure mathematically, things like that. So yeah, lots of ways of tackling.
So Minecraft would be another good one on that, with its constant iteration of its software, so you could talk about how that updates.
Yeah, well, and of course agile methods are very popular, very widely used, and it won't be hard to find a company that's using them. Most companies that I know of use some kind of agile method. And one of the more popular general approaches is called Scrum, which is actually named after the game of rugby. There's sort of a bit of a misunderstanding about what a Scrum is, but that's okay. Yeah, but we'll talk a bit more about that tomorrow. That's the 6 areas. Yeah.
Could some of this be used in that other achievement standard of 3.14?
3.14 is...
Explore in depth.
It's the technical
yes.
the technical one?
Yes, oh, sorry, yes, I'm sorry, I know what you mean. Absolutely, and in fact, there could be a topic in here that you just make a 3.14 topic. And the difference with, so 3.14 is explore a technological technique or something. Yeah. And in fact, at one stage when AI wasn't in this list, Heidi developed a whole lesson plan for 3.14 for doing AI in it. And then it got back in the list, so we're adapting it back for this. And because the different criteria. I don't think you want them to do the same one. It's kind of a bit of double.
No, I'm just saying some of the content is potentially what they could use.
Yeah, so I haven't got the criteria in front of me, but this would be lifting the lid off and looking at these particular issues, whereas the other one, I think it's a bit more about applications and things like that. But yeah, so a slightly different angle on the same topic. Yeah. Different criteria might suit some of your students better than this one. Yeah. And it's bigger too, right? It's several credits.
No,
4.
4? Yeah, but...
And it actually came out of this.
Right. So that's 4 credits. Each of these would be 2 credits. Because it's 4 credits for the whole standard, and they have to do 2 topics. So they would be doing twice as much. Theory, whatever twice as much means.
They could do this and that, that's what I'm saying. And
Yeah,
the material
for sure.
is there.
Yeah, and you could make quite a focused course that way. Any other questions or suggestions at this point? Okay, cool. That's the overview. Now, actually, what we scheduled now is, and one of the things we got in the feedback last time is people enjoy hearing from students and their stories. And Heidi.